Hi, I'm Geoff Clarkson. In May of 2023, I was asked to lead a project team to develop a new part on assessment of fiber-reinforced polymer, or FRP, equipment for API 579, the Fitness for Service code. In April of 2024, I provided a live online seminar to members of the API Fitness for Service Code Committee to provide education on FRP. The session covered material on design using FRP, damage mechanisms experienced by in-service equipment, detection of damage, and overview of repairs, and monitoring in the contents of planning for a part in API 579 to assess fitness for service of FRP. The live session is being recorded here to be available as an ongoing resource for the API 579 committee. Since the initial session, some questions have been raised that provided opportunity to add some additional explanation. Slides with this additional explanation have been included in this presentation. This video is the second of 4 videos. This is the agenda for the videos. Video 1, already completed and available, is the introduction to FRP design. Video 2, this one, covers FRP damage mechanisms. Video 3 will be non-destructive evaluation to detect FRP damage. Video 4 discusses remediation, mitigation, and monitoring of FRP and the proposed FRP part for API 579 ASME FFS-1. The key items to discuss and understand regarding damage mechanism for FRP are listed here. First is long-term behavior is nonlinear. 2, damage reduces material properties. We actually have a change in the physical properties of the material as a result of damage. 3, there's no documented evidence that relates the appearance of FRP to the damage level that it has experienced. 4, the flexural modulus actually is used to show the extent of damage. And 5, the retained flexural modulus provides fitness for service engineering inputs. Damage can occur to FRP in the polymer, the bond of the polymer to the reinforcement fibers, and to the reinforcement. As discussed somewhat in the design section, but reinforced even further in this section on damage mechanisms, FRP composite materials are nonlinear viscoelastic materials. The polymer, glass fiber, and carbon fiber are nonlinear viscoelastic materials. Stress or strain causes reduction in strength of the material. Chemical attack, which is often described as corrosion, does a couple of things. The primary effects are that it reduces the Young's modulus and strain at failure of polymer, so therefore it reduces the strength in both the modulus and strain component, and it reduces the strain at failure of glass. Further discussion on nonlinear viscoelastic materials. For glass, the data that we have shows that the strain at failure in an inert environment nominally declines to 55% to 65% of the failure strain for new. The Young's modulus, the elastic modulus of the glass reinforcement fibers, remains constant. So you could expect a fairly constant strain environment for structural FRP. The thermoset polymer sees creep from applied stress, so you get a small amount of dimensional change, relaxation, which is modulus reduction from applied strain. The strain at failure also declines with modulus reduction, and both can result in a fairly small, like about 1% dimensional change in the material under service conditions. So typically, the effects of damage I'm showing on this slide, when it comes to mechanical stress or strain, this is similar to developing a hydrostatic design basis for equipment. You'll notice that we have listed here on the vertical axis the percentage of new strength. This way, the two different FRP structures are shown here with different new strength values, total new strength values. So I've normalized them to percentage. You can see that the strength drops off fairly quickly under this environment where we're measuring the time to a leak or a crack, and you can see the data points showing that as we reduce the amount of stress, which would be from internal pressure, as we reduce the amount of stress, it takes longer, and in fact logarithmically longer, to produce a crack. That's how we develop a long-term hydrostatic design basis. For chemical attack, we also see the same type of behavior. If we take a look, and this is something that's really done primarily for polymers, although I'm going to present some information later on glass fibers as well. But you can see that retained polymer strength, of course, new and undamaged by any chemical attack, it's at 100%. And for a variety of different chemicals I'm showing here, we have a set of retained polymer strength data. And you can see it covers a fairly wide range because it is related to the chemical that it's applied to. And you see in both cases, we see this logarithmic reduction in strength of the material. This applies to polymer, reinforcement, and of course their combination in FRP. Thickness loss is a huge, important consideration for steel and metal alloys. It is not nearly as important to FRP. It is not a common damage mechanism on its own. In fact, it usually only comes from abrasion or oxidation, or perhaps from weakening or damage to the chemical as a consequence, or of the polymer as a consequence of chemical attack. It's directly related to polymer damage, and it's usually from chemical attack. Most FRP actually retains constant thickness throughout its life, even in some of the most corrosive environments, such as hydrochloric acid. Damage progression is shown here as changes in the construction properties, the properties that are used nominally for design or considered in design. So I'm showing a percentage of construction values where, of course, at new, everything is at 100%. And we can see that normally the thickness, shown as the green line, will stay pretty much constant. FRP tensile Young's modulus. This isn't strength, it's modulus. The Young's modulus in tension will decline by maybe 3%. You can get a decline of 20% in very, very weak FRP with very little glass reinforcement. The Flexural Young's modulus, different from tensile Young's modulus. The differences are actually discussed in the first video. Will decline in this logarithmic with time in service. And in fact, what we'll see is as the flexural Young's modulus declines, we get a corresponding but even deeper decline in the strain at failure for the polymer. And this is not this is not a universal number. What I'm showing you here is the 5th percentile of data that has been accumulated for fairly benign chemicals, for example, water, dirty water in particular, like basically groundwater. If you're storing that or you're exposing FRP to that, you may actually see minimal change in the polymer failure strain. However, if we're dealing with, for example, sodium hydroxide solution, we'll see a deeper or a steeper drop and a sharper drop. So it's chemically dependent. We're showing the 5th percentile for a group of chemicals that have been tested on polymers. And the reason we're doing that is to be conservative. Polymer is usually the first to experience damage. For those of you who've watched the first video, you can see a discussion on this particular cross-section, which is talking about which is describing and showing portions or cutouts from a video of a tensile test of a fiber reinforced polymer coupon. And you can see here, this is in the final stages. We're still not at the tensile strength of the specimen yet because the fibers have not yet failed. But you can see how we've got cracking throughout the polymer. So the polymer has failed, but the fibers have not yet failed. We're actually, and I'll discuss this a little bit later in this video as well, but we normally will consider that cracking in the polymer is failure initiation, and that's the point that we work toward. Polymer is usually the first to experience damage. It will also affect the bond with the sizing on the reinforcement. As we talked about formation of glass and polymer, and as well carbon fiber and polymer very seldom will bond together. We need a sizing or a primer in order to provide an interface zone where that bond can occur. The polymer will usually fail or fracture before the reinforcement, which we're showing here. The cracks and leaks actually occur in the polymer. When you get a leak or a loss of containment, it's almost never because a fiber failed and the polymer is intact. It's because the polymer has cracked or fractured. And when we have significant weakening of the polymer, we also get changes to the Poisson's ratio. And that's not understood at this time. Not at all understood at this time, and no one has produced any data on that to date. And we also get failure of the bond to the reinforcement. So therefore, we can actually have fibers slipping in the matrix of the polymer. Damage progression is not usually uniform through a section. Just like thickness loss in steel, where thickness loss is generally initiated at a surface that is affected by some process condition, we have the same thing happening with FRP. So zones with chemical exposure, or if there is higher stress in a particular zone or strain, those zones will be damaged first. And I'm showing here a cross-section of a cutout from an FRP shell that has been used to contain hydrochloric acid. You can see that this is a 28 millimeter thick piece of FRP. There are no visible cracks on the process side, none. And in fact, when you look at the process side, I don't actually have that picture here, but when you look at the process side, it's slightly darkened. You can see this thin layer, but there's nothing in particular that tells us that we have any particular damage. This is a cutout. We don't usually have cutouts available for a fitness for service assessment because we need non-destructive methods. Otherwise, we have to requalify the equipment. We can see that We have some visible effects from service here, and that's the green color. That green color forms with, as a result of reaction of the contents of the equipment with some ingredients or constituents of the polymer. And as well, we have this zone, which looks just like it did when it was new. There's no visible effects from service. So we actually have a very thick remaining portion of the FRP that doesn't look like it has any issue at all. The properties are still, they really become an amalgam or a mixture of the damaged area and the undamaged area. It's really important to talk and understand failure initiation. Cracks in the polymer occur when the polymer component for structural performance of the FRP has failed. This goes back to the slide I showed when where we showed the tensile test cross section, and we have cracking in the polymer. We're not anywhere near the tensile strength when that polymer has failed because the reinforcement dominates tensile strength. However, cracking has occurred. We're seeing failure initiation at that point. It almost always precedes glass fiber failure. And that's nominally because glass fibers, believe it or not, have a higher failure strain than most thermoset polymers. There are a few thermoset polymers available today commercially that have got fairly high strain at failure values, and so therefore they're likely to not crack when new, to not crack when the glass that they contain fails. However, they're relatively rare. With rubbers, which are also thermoset polymers, with cross-linked rubbers, we also will have a fairly high failure strain. But for most structural FRP, the failure initiation in the polymer precedes glass fiber failure. The service limit, or the end of life, is the point where cracking could occur in the polymer of the portion of FRP that is required to sustain the operating loads. If we recall back to the previous slide where we had a large or a fairly thick remainder of that FRP that at least has the appearance of being undamaged, and I can verify that it is essentially undamaged, but that has the appearance of being undamaged. That fairly thick zone is still, it would be considered the portion that is sustaining the operating loads, and it is probably even more than we need to sustain, more than is required to sustain the operating loads. So you've still got excess material in that condition. I'm going to talk for a second here about how we get to a crack, because this is important. It actually shows the process by which cracks will often develop in FRP. So I've actually listed a strain value here. We could actually normalize it and make it a percentage of original strain. But nominally, for a lot of polymers, the failure strain is going to be around 3%. And by the way, for glass, it's around 4%. It's up here. And that's when it's new. What happens is that in fact, you almost always only get these values, the new strain at failure for the new or newly formed material, polymer or glass. As we apply service conditions, what happens is that we get relaxation and creep in the polymer of the material. And what happens as that relaxation and creep develops and grows, we see a steady reduction in the strain at failure. That's what this curve is showing, is the strain at failure of the polymer. You can see that as long as it's above the operating strain, which is the strain in the pressure boundary shown here, as long as it's higher than that, then we're not going to form a crack as a result of service conditions. However, at some point in the future, we will get a crack. Now, what happens is, as a consequence of creep and relaxation, we see changes in the amount of strain that actually occurs in the pressure boundary. And so this has got a very, very slight upward slope. And in fact, if you see, if depending upon the excess capacity that's built into the design, and notice that with FRP, we will often have somewhere like a factor of safety of 10, which is why I show that the nominal strain in the pressure boundary here is 0.3% compared to 3% for the new material. This crack usually initiates in the layer exposed to the most extreme conditions. For example, in something exposed to chemical attack that accelerates this change in those layers, perhaps on the process side. Now, the important thing is when the pressure boundary, when the minimum thickness of FRP in the pressure boundary is exposed to this strain level, that's where we can have a failure initiate. This chart also shows that for these materials, we have both creep and brittle behavior that are occurring at the same temperature and in fact in part of the same process. What we have is creep producing this curve and brittle failure, brittle behavior, and fracture occurring here. So it's this material, these polymer materials in particular, and as well the glass materials as well, can show this, that we can have a fairly significant change. Crack progression is also quite different in FRP. I've highlighted the cracks here because it enhances the contrast that we have available. This is from a sample provided courtesy of XPS in Ontario. And we have a crack forming in this darkened layer of FRP. This is actually from a duct exposed to sulfur dioxide off gas from a smelter. And the cracks form in these embrittled areas that are on the inner surface. They're exposed to the highest temperatures and the greatest chemical attack from sulfur dioxide, which is relatively benign for FRP. And these cracks form, but what happens is, as the crack penetrates into the material, it does not propagate the same way that it would in a metal alloy. In a metal alloy, we'll often see the crack propagate as a consequence of or normal to the stress direction. But here, we get to the point where this crack comes to material that is stronger and resists the crack propagation. So the crack literally turns and spreads out. So this actually produces a large number of planar indications that a lot of people would think of as defects in metals, but that it just really indicates crack depth in FRP. We'll talk about that in the NDE video. We also have a number of overt flaws that can occur, delaminations and blisters in particular. To be honest, most of these originate at the construction of the FRP. They're often not, they may not be detected at construction, or they may be ignored. This in fact is a direct consequence of a curing error. And these are consequences of formation errors. They left some voids in place, or they didn't appropriately prepare some surface as they built it. There's only a minor effect on fitness for service of FRP. Really, there is. This is not where we need to be focusing our attention. Within these visible features, we can also have color variations. So I'm showing some labeled here. And in fact, in these situations, the color variation, this is from dirt accumulation that has diffused into the FRP from the process side. This is from some mild chemical attack that's occurred on the process side. This is probably from a manufacturing feature, and we actually think it was just an excess. It was a finishing layer that was applied too early. So it's not. It also doesn't play any role at all in making this FRP fit for service or not. There's no direct relationship to damage or fitness for service from any of these color variations. There's no documented evidence that allows us to make a determination as well. We have some visible things perhaps in the surface. We have some voids here in the surface. We have some areas which may have poor resin or polymer saturation of reinforcement. That's what these white areas are. While they are not normally accepted by construction codes, they still don't affect fitness for service of in-service equipment. So how do we measure damage? Well, one of the things that we've covered is that visibility cannot provide data for assessment of fitness for service. Also, what we can use is the retained Flexural Young's modulus, or RFM. That can actually provide direct engineering inputs for assessment. Recall this slide from earlier, where in service we can see changes that occur in the Flexural Young's modulus. Now, these results are generally provided, or they can be provided by a destructive test, which also means you have to remove a cutout from the material. You need a representative destructive test for any affected zone. It could become very expensive and prohibitive in terms of determining fitness for service. Non-destructive evaluation to detect these changes is what we want to do, and we'll deal with that in the next video. Retained flexural modulus is defined as the current Flexural Young's modulus divided by the theoretical flexural modulus. This could be the new flexural modulus, but in many cases we don't actually have this reference value for new. But we can have a theoretical flexural modulus if we need it for a sample, and there are methods to do that, which I would be happy to discuss with you. The current Flexural Young's modulus is available from either a destructive 3-point bend test. The test that we like the best is given in ASTM D790, or a suitable non-destructive evaluation method. Because we're only dealing with Young's modulus, we don't need the issue that they deal with for D790, where they also tend to report flexural strength, which is, to be honest, a fairly meaningless parameter. It requires a certain length to depth ratio. We can actually forego that requirement because we're only looking in the linear zone for modulus. And the theoretical can come from classical lamination analysis, which we described in the first video, described very roughly in the first video. You can also use test results from new FRP, which is what I mentioned. So what does it show? What does RFM show? It shows the total results of changes to the polymer in the specimen. Now, this is actually affected by changes in the shear modulus, the Young's modulus of the polymer, and the Poisson's ratio of the polymer, as well by the strain at the fiber-polymer interface. And in fact, changes to the Young's modulus of the polymer will actually directly change the Young's modulus in the Z direction, because the Z direction normally has no fiber reinforcement that travels in this direction, and the fiber reinforcement is almost only in the plane, or because we build it in layers. So this, we're really only dealing with the polymer Young's modulus and whatever fraction of the volume is occupied by glass fibers, which are reinforcement fibers, which is it's a relatively small thing, but it will actually change a little bit what the value of the gross value of the Young's modulus is. These changes, the changes that occur as a consequence, are not modeled by classical lamination theory. And in fact, the reason that they're not modeled by classical lamination theory is that we actually start to see a few things take place. And I'll show you on the next slide what happens with that. The other thing is that the geometry of the specimen, and this is why Timoshenko came up with the method that I showed on the previous slide. The theory is that all of the surfaces retain their relative position. So the ends retain these nice perpendicular to the neutral axis orientations. But you can see from the previous slide, Timoshenko basically came up with a description that says, hey, wait, the ends actually do not retain their same geometry, and as well, the neutral axis actually shifts as we bend it. So that will affect a couple of things. The cross section will also change, and in fact, that's what we're showing a bit here. The test method that's used to measure for destructive measurement of flexural modulus actually assumes that there will be minimal change through the thickness in this direction, okay? But in fact, we've actually built a model here where we have applied that 3-point bending load to the midpoint, and you can see we actually get a deformation. Now this is a slightly extreme example because we have a small load application area, but you see how we have this deformation area delta, which is added to delta Z. So what happens is that the displacement of the head is measured as delta plus delta Z, and so the flexural modulus is determined as a consequence of two of those, and this occurs more with damaged polymer than with undamaged polymer. So we're basically seeing a large contribution by the Young's modulus of the polymer, or essentially the elastic modulus in the Z direction. The other thing that's really important to understand is that even though we use flexural modulus to determine the extent of damage that has occurred to FRP, the RFM value is an indicator. It is not a property. It indicates the amount of damage that has occurred to the polymer in the FRP. And in fact, fracture or strength represents that transition from elastic to inelastic. So what we're looking for is to use this indicator to find where at what strain level we will see that failure or fracture. When we quantify damage, we assume that material is still elastic. Because once it's no longer elastic, it's probably failed anyway. We want to make sure that it's still elastic, and we're trying to find its elasticity limits as we quantify the damage. And RFM has different effects on tensile and bending properties. And that's because tensile properties are dominated by reinforcement fiber, and the bending properties are heavily influenced by the polymer. They're also influenced by the distribution of the reinforcing fiber, but the polymer is, from the previous slide, the polymer will definitely show you what it's doing at that point. And the way that we relate this indicator, RFM, to fitness for service is through structural evaluation of the polymer. We want to find the point where failure initiation or crack formation will start in the polymer that we're looking at. So what we're looking for is, for example, for a given value of RFM that we've determined from a sample. If we find it along here, we can look straight up and say, okay, so the retained polymer strength is, say, about 10% of what it was, and the strain at failure is 30% of what it was. And the reason is that the strength is a consequence of the retained elastic modulus of the polymer, which we can approximate by the same as RFM, and we multiply that by the percentage of retained strength, and we come up with a value for or percentage of the retained strain, and then we can come up with a percentage of the retained strength. We can take this back to our stress analysis through the section looking at intact FRP to determine if we have a situation where failure is going to occur. Damage limits are required for assessment. You have to know what the endpoint is. So what do we consider? Well, the range of polymers that can be used, and there's a really wide range. Data available on polymer changes. So what data is available that gives us the relationship of change in failure strain with RFM or polymer modulus? The estimate of the factor of safety of the equipment, and we talk about that a little bit in a minute, but the original factor of safety that was used for design would be nominally 10, but if the installation has pressure management problems or loads are not as stipulated by the design or assumed, or we have an effective loss of thickness or a reduction in available structural thickness of the material, then that will change the factor of safety, the effective factor of safety. Then we will have physical test data of the FRP in service, whatever we have, and engineering experience from failure analysis and equipment reliability. This engineering experience has to be quantitative. It has to be something that where we can provide measurements, data, and calculations, of course. The critical RFM is the minimum allowable RFM that can be allowed for a given condition. Developing that, what we look at is we say, okay, so we know for a factor of safety of 10 that nominally we're allowing a design stress of 10% of the ultimate. We're allowing a design strain for 10%, or that is 10% of the ultimate strain at failure. So if we come over here and apply this value at 10%, we can say, okay, so that at a factor of 10, we have 10% of RFM. RFM at 10%, give or take. Actually, it's about 12%. This actually starts to look a little bit complicated, but essentially what we've done is we've constructed this curve based on the strain expected at different design factors of safety and what is the RFM value that is expected by plotting against the fifth percentile failure strain curve. And that's the curve that we've developed from data. In fact, this is essentially the same curve as the one I showed where we have RFM on the bottom and percent of retained strain, but it's rotated. So when we work backwards with that curve, we can produce this. And this is for tensile situations. For buckling situations, we actually have, interestingly enough, an elastic instability onset curve that is below the tensile curve in terms of where the limit is. And this one is actually more limited by elastic modulus than by strain. That's why it's different. And realistically, from a practical perspective, the lowest value that we've measured for retained flexural modulus from any in-service FRP equipment that we've dealt with is 36%. Now, there are values for chemically exposed coupons, and only chemically exposed coupons, where we've seen RFM values of 0, but there was no way that first of all, those coupons were actually designated and looked at for the purpose of not providing any kind of structural performance. They were only as protective, looking at the protection afforded by the polymer, not for the structural properties. When it comes to any of the other samples where we've had a structural requirement for the FRP, the lowest that we've ever measured was 36%. And believe me, it was in very poor condition. It was not structurally sound. So we're using this as the minimum practical limit. So the critical RFM curve looks a little bit different. It's a little bit different for elastic instability as it is for strain bases. And that's partly because elastic instability doesn't require quite as much conservatism. And the other thing is, realistically, the nominal factor of safety that would be used for design is a minimum of 5 for elastic instability problems or for elastic instability applications, and 6 for tensile. There are a couple of codes that very specifically use 6 as the starting point factor of safety, and many use 5 as the starting point factor of safety for elastic instability onset. So the reason for this is because we can now say if we determine the factor of safety for equipment, we can then, or the real factor of safety for the operation of equipment, we can then use that value to come up with the required minimum or critical retained flexural modulus for it to be fit for service. And that would be at a level 1, for example, for those of you who are familiar with the different levels of assessment in API 579. So what this means is that, for instance, for a factor of safety of 4, we have about 60% or an RFM of about 60% as the minimum acceptable for elastic instability and about 65% for the strain basis. And you can use that. So if you've actually got an effective factor of safety of 4, we now know what we can work to for the equipment, or what we can work to for acceptance. These curves show all the way down to a factor of safety of 1. It doesn't mean that we actually promote or would ever promote building any equipment with a factor of safety less than these values here, that 5 or 6 that we would normally use for construction codes. But what happens is that the effective factor of safety of equipment can reduce because it may be exposed to pressures that it wasn't designed for. It may be exposed to or operating conditions it wasn't designed for, and we also may have a change in available thickness for handling the stresses. Remaining strength factor is widely used in API 579. And it's defined, I think part 4 does this the best. It's the collapse load divided by the collapse load for the damaged component divided by the collapse load for the undamaged component. What happens is collapse often occurs long after we actually have a problem with the pressure boundary failure in FRP. Okay, because a pressure boundary failure can occur well before collapse occurs because we have cracks form in the polymer. So the RSF, or remaining strength factor for FRP, is also basically equal to the current factor of safety divided by the as designed factor of safety. So that's why in the previous chart, when I showed what is the actual factor of safety of operation, we can use that chart to find what the acceptance criteria are for that situation. When we do that with FRP, that RSF value incorporates operating conditions and the remaining structural properties of the equipment. That's essentially what we're looking at for it. An overview of this damage discussion. The damage to FRP is completely different from damage to metal alloys. There's minimal change in thickness. Inspectors cannot see most damage that has occurred. Visual inspection methods cannot detect the damage mechanisms. They can detect consequences of that. You cannot deny an inspector who says, look, there's a crack. And the standards used for construction do not apply to in-service FRP. That's extremely important. The visible defects or the visible features that we identified earlier in this presentation are things that would be rejected by a construction code. They don't apply to in-service FRP. There's no relationship that's ever been demonstrated. All service conditions, that's stresses, strains, temperature, and chemical attack, make the resin or the polymer weaker. Resin or polymer damage occurs before any damage to the reinforcement occurs. That is a very, very common feature. And critical RFM is the minimum allowable RFM, in particular for level 1 assessments under API 579. So let's continue with this example a little bit. If you paid attention or if you've been able to watch the first video, you'll see at the end I presented a design example for a scrubber with 5%, or to be used for a 5% hydrochloric acid scrubbing liquor. And this is after about 16 years of service. The appearance of the inner surface, well, looks like this. Looks pretty rough. And in fact, you can see all of these cracks here. And you see how the cracks come up. You can actually see in this one how the crack has penetrated into the surface and then it's starting to turn. We don't have any visible cracks in this cutout behind this discolored zone. Okay, the overall thickness is about 16 millimeters. That's compared to 16.3 that we determined in the design criteria. That's pretty close. And using the ASTM D790 test, the retained flexural modulus of this specimen is 57%. This is the end of video 2. I invite any questions. Contact me on these coordinates. I'll be very, very happy to answer you. And in fact, you never know, it might actually end up with an update to this video if the questions are warranted. Thank you very much. I appreciate it.